So if you want to know the future in the U.S., you just go over to Asbury Park and talk to Madame Marie. So what I'm going to talk about is what Madame Marie reveals about the future of human genetics, with a focus on fulfilling stakeholder requests. So I thought Matt's comment yesterday was quite apropos. The only stakeholder I'm not going to talk about too much is pharma, because we had people cover some of that yesterday. And if you've ever had your fortune told by Madame Marie, you know that she vacillates on her dates a lot. So she wouldn't tell me too much specifically about the dates. But a key stakeholder for us are physicians. And if you ask physicians what they want from genetics, you get a whole variety of answers. But the most common one is, just don't make my life more miserable. So we have the traditional genetics and genomics now. That's not going to go away. It's an expanding iceberg. So it will be bigger now, this top part. It will be bigger in 2023 and 2028 than it is now. But there'll be a whole under part of the iceberg, the 90%, that is computational and decision support. In the US, 50% of practicing physicians have never had a course in genetics. And 35% of medical schools don't include genetics as a course, which is a combination of medical schools where genetics is incorporated into every class that they offer, and those that still don't find a way to get it into their curriculum. It has to be the case that much of what we do for translation will come in this space. The things that we do underneath in the iceberg to create easy to understand instructions, content for physicians to take care of patients in better ways. Other stakeholders include medical centers. And if you ask the medical centers what they would like genetics to do for them, their answer usually has to do with things that are very expensive for them, very difficult for them, things that tend to be more common, and things that they already do a lot of work in. So we already do predictive modeling in the ICU to watch, try to understand what patients are going south. And they would love to know, can genetics help? These are things where incremental improvements can have a big return. An iota of improvement in the predictive modeling that's already done every day in medical centers, trying to find patients before they go south, before you get that crash card out. That's all they're asking from us, is a little bit better than what it is now. Well, sepsis is in the top 10 of the most expensive conditions in medical centers. And right now, the best predictor of the development of sepsis is people who are old and sick are the most likely ones to develop sepsis. But of course, septic shock kills younger people, and if we could improve the predictive ability of who among young and relatively healthy people develop sepsis, that's a big win for medical centers. When Vanderbilt achieved a reduction in the number of patients with infection who get admitted, a relatively small percentage reduction in the number of patients who don't get admitted to the hospital and never develop out of hospital sepsis, that was considered a huge win. If genetics allowed that fraction of patients to be a little bit smaller yet, it would be considered a big win. It's a major reduction in healthcare costs. Insurance companies have their own interests, and when I've been fortunate enough to be part of a group that talks with executives from insurance companies about genetics and genomics. And what they keep saying is, stop BSing us about what genetics is going to do for us. Play it straight and tell us how you're really going to improve care and reduce costs. Now, as Matt said, we all live in our own ecosystems, and insurance companies in the US have a different, every healthcare system is different, and private insurance is a bigger part of ours. But I think one of the overlooked opportunities that Matt and Marie forecast was the ability to improve biomarkers. So we use a lot of biomarkers in medicine. Virtually all biomarkers that we use have a genetic component and a non-genetic component. For some biomarkers, LDL cholesterol, those two things work in conjunction pretty well to predict what it is that we want to learn about LDL cholesterol, the risk of heart disease and cardiac events. But there are many biomarkers. Cystatin C is an example, but there are many where the genetics is noise for why we use the biomarker. We would have a better biomarker if we conditioned out the information on genetics for many of these biomarkers. There's a subset that we know about where we are basically measuring with error metabolome proxies of rare coding variants, and we would do better to just use the coding variants. There's a number of biomarkers where what we really want is the delta, the difference between what the genetically predicted biomarker would be and what we actually measure. Some metric around that delta is probably what we need for about a third of the biomarkers that we've got at scale in BioView, at least, on patients. And we have a lot of difficulty with ranges and thresholds because we create health delivery disparities right now. Because many populations, the biomarkers, measurements that we make, can differ by historical geographic ancestry. And right now, the best that is done in the US for this is to condition on race, which it's not about race. It's about allele frequencies that differ by historical geographic ancestry. And not infrequently, what we have is the tendency to reorder tests, order additional, effectively, additional kinds of tests, because we have large minority populations whose average values differ sufficiently from the ranges and thresholds that we use that we end up costing them more money. It's a crazy, crazy thing. And it's in our power to alleviate a lot of this with relatively simple approaches that can be pioneered in a CDC. Not to be left out, we do offer, Madam Marie was sure, we do have long-term job security for medical coders because with something like the CDC, it will be possible to envision diagnostic codes that are not sort of randomly related to physiology and organ systems, but organized by genetic architecture. So the ICD Genetics 2 release will include degree of shared genetic architecture to nearest neighbor, ordered clustering of known causal chains, and an overlay of shared pharmacological effectiveness based on known genetics. And then, scientists are stakeholders too, and the opportunities for new kinds of discovery in a unification of biobanks and common disease and the common disease consortia, and the ability to iterate between those two and just the very large-scale health records that are available often in conjunction with biobanks, really should give us a lot of additional insights into the correlations among phenome and the reasons for those correlations. I think the more data we have, the more we realize what we could learn if we had even more data, the more we realize we don't know but can learn. And so I think some of the headlines that she projected on the ubiquity of pleiotropy in the human genome and harnessing pleiotropy to power more genome discovery, I would like to think could come true with a consortium like this. So I know we all have enough calls, we have enough meetings, but I think that there's some real opportunities here for new kinds of science questions, a lot richer environment for conducting our research. And so the rationale for, there is a rationale for starting yet another consortium. But I'm happy to take questions and comments.